Welcome to the next video. Let us continue the discussion of turbulence modeling and let us see what is being written over here. The first point is that it is unfortunate fact that no single turbulence model is universally accepted as being superior for all classes of problems. So this is what I mentioned in the previous video, that there is no guarantee that always the specific model can be suitable for all the type of flows. It is really not like that. It depends on the application. It depends on the kind of simulation what you're trying to do. All right, so we have to compromise between the amount of computational power which we have and the the relation between the actual physics, like what are you trying to depict in this flow simulation, and based on that you have to decide as to what turbulence model is suitable for your particular case. So this is a quite decision making task, and we have to consider this task as a very significant, in a very detailed manner. We simply cannot select any random model because we are reading over here that it is an unfortunate fact that no single turbulence model is universally accepted. So we cannot say this, that the manual itself is telling us that there is no single turbulence model that can be suitable for all the flows. We cannot go with this statement, and we cannot directly select any random things. There must be a reason for that. Either we have to read some existing papers and see whether they have proved through experimental comparisons that so and so model was suitable for so and so type of flow. So if that is available, then we must also try to depict the same way, and we must also try to validate our numerical simulation results with that particular model as well, and then only we can decide to proceed with that turbulence model for the consequent simulations. So this is a quite decision making point when the simulation stage for us. And the next point states that the choice of turbulence model will depend on considerations such as the physics encompassed in the flow, the established practice for specific class of problem, the level of accuracy required, the available computational resources, and the amount of time available for the simulation. So these are the factors which are contributing for us to make a decision, as I've mentioned to you, and that is what is being written over here. To make the most appropriate choice of model for your application, you need to understand the capabilities and limitations of various options that are available to us. So we have to see which, obviously by reading through papers, by reading through articles and manuals, one will understand what are the capabilities of a turbulence model and what are the limitations of a turbulence model. And based on that, we may decide as to which one we can consider for our case. All right. Now let us move to the next page. So this is what we are doing actually. Like, we are converting the Navier-Stokes equations into Reynolds-Averaged Navier-Stokes equation, right? So I'll just go to this website over here. I'm sorry, yeah. So you can see that the Reynolds-Averaged Navier-Stokes equations, or they are called as RANS equations, are time average equations of motion of fluid flow. That is what we have discussed, that we are time averaging the NS equations and we are converting it into a modified set of equations, and those modified set of equations are called as RANS equations. And in that RANS equations, there is an unknown variable which has which came up, and we have to solve that unknown variable. We have to model some other set of equations for solving that unknown variable, which which came out by modifying the NS equations, right? So this is quite tricky. Just try to focus and understand. So the idea behind this equations is Reynolds decomposition, whereby an instantaneous quantity is decomposed into time averaged and fluctuating quantities, an idea first proposed by Osborne Reynolds. So Reynolds is one of the prominent person who has contributed immensely in fluid studies basically. So he was the person who has suggested about this thing as well, that is the conversion of NS equations into RANS equations. So RANS equations are nothing but the modified set of equations, and this is what we are doing, in that we are decomposing the equation, and we are converting the instantaneous quantity into time average and fluctuating quantity. So this is something difficult to understand. I have some another PPT for you to show, don't worry about it. So let us just complete rest of the para. The RANS equations are primarily used to describe turbulent flows, right? And most of the applications, whatever we deal in our projects, in our research, or in our studies, especially when we are utilizing CFD, we will be having the presence of turbulent flow. So it is not like we cannot run away from this turbulence model. We definitely have to include the turbulent model in our cases, unless we are having a low Reynolds number laminar flow, right? So in that cases only we can just ignore the turbulent model and we can go with the inverse kit model. So that will be like, you'll not be having any turbulent flow in your case. So maybe you're just avoiding the turbulent model in that particular cases. But the kind of projects what we deal and what we try to depict with the real-time projects or the real-time case studies, in those case studies turbulent models is required, right? And one has to understand what is turbulence model before using it. Without understanding what is it, if you are using it, you will not know anything. In the software, it is a simple click of the button. You just have to click and choose among the list of turbulence model available with us, right? So that can be shown with 1 minute in 1 second only. You just have to go and click so and so model, then you just have to solve it. But what is happening? Are you understanding what is the purpose of turbulence model? No. So that is the reason I'm just trying to build your foundation in a detailed manner, and please try to understand what is it. Okay. And so these equations can be used with approximations based on knowledge of the properties of the flow turbulence to give approximate time average solutions to the Navier-Stokes equations. For a stationary flow of an incompressible Newtonian fluid, these equations can be written in this form. So this is a form of equations that can be written. All right, we'll jump to this presentation over here. Now what is mentioned over here was, I'll just 1 second, I'll just pull up over here. Yeah, you can see it is mentioned over here that in this equations, in the conversion of this NS equations to RANS equations, we are performing a Reynolds decomposition technique. Okay, and in that we are replacing the instantaneous quantity is decomposed into time average and fluctuating quantity. Okay, so these are some new words for us to understand, and we will see what is it. Okay, now what's present over here is an ANSYS presentation which I had in my mail since a long time. I'll attach it in the resources, and it is a kind of 40 pages 48 pages presentation. I'll show you as we proceed, don't worry about it, but let us just try to see what is mentioned over here. Okay, so this is the case backward facing step. Just imagine you have some flow which is being coming from the left hand side and moving on the right hand side. Okay, now what's happening is in reality, this can be the actual structure of your flow when it is coming from the left hand side, and because of a sudden step present over here, the oncoming air can try to convert itself into this turbulent manner, right? So this is how it can be the actual instantaneous velocity contour. Okay, so this is how your air velocity can look like. Okay, so we have certain recirculation zone over here. That means the air velocity is pretty lower here, and since the air is coming from the left hand side on this step, it is a little higher in this region, right? And you can see that the complete flow is turbulent in nature, right? It is having the presence of plenty of fluctuations or eddies, we can call them, right? So this is how it can be in actual reality, right? Now let us read what is mentioned over here. As engineers, in most cases we do not actually need to see an exact snapshot of the velocity at a particular instant, right? So at a particular instant, we are really not interested, or we do not want to see the actual thing what is happening over here. Instead, for most problems, knowing the time averaged velocity and intensity of turbulent fluctuations is all we need to know, right? This gives us a useful way to approach modeling turbulence. So we are eliminating, or we are resolving this eddies, and we are just looking at the time averaged velocity contours. So this is how, I'll just go down. This is how is a time averaged velocity contour, and this is how you will be getting the contours in your CFD simulations as well. So we are getting the time averaged velocity contour. So I'll just try to make you understand what is the time average and what is instantaneous with the help of this graph, which is present in the next page. Okay, now if you just imagine you have this real flow, and you just put a point randomly over here. Just imagine you put a point over here, and you are measuring the velocity at that particular point with respect to the time, right? So since this is a pretty turbulent flow, the velocity will not be constant. It can be either increasing or decreasing, or it can be constant for a time, again it can decrease, then again it can go up, right? Because the flow is turbulent in nature, right? So it will not be constant, right? So what's happening is, if you are plotting that particular velocity with respect to time, then you will be having this graph. Okay, you will be having the x-axis with time and the y-axis with velocity, and this is how your velocity can look like: the fluctuating velocity what you are having, the instantaneous velocity what you are having, right? So the for example, if I'm just considering this point, I will be having this particular velocity field. This is what I'm just trying to mention you over here. I said you that the velocity can increase, the velocity can decrease, and the velocity can be constant. It can again go down, again it can come up, right? That is what is happening. It is decreasing, then increasing, going down, being constant, moving up, again being constant, coming down, again constant, moving up. So this is a fluctuating instantaneous velocity, we can say, right? So that is what is mentioned over here. If we recorded the velocity at a particular point in the real turbulent fluid flow, the instantaneous velocity u, so we are lettering this instantaneous velocity with capital U, would look like this. So this is how your velocity will look like, right? Now what are we doing is, we are creating a time average velocity. You can see this straight line over here, right? Can you see this straight line? So this straight line is called as a time average of velocity. So whatever is the instantaneous velocity, we are just averaging it, and we are creating a straight line, and that is called as the time average of velocity. And this is written with a u bar or u dash, or you can call it u over bar, whatever is it. So this is the average time velocity. When we are converting this instantaneous velocity into a time average velocity, then your time average velocity will be a straight line. All right, now at any point in time, the instantaneous velocity will be equal to the time average velocity plus fluctuating velocity, and fluctuating velocity is represented with u prime, and you can see that this distance over here, right? So that is the fluctuating velocity. Now for example, if you want to if you really want to measure the velocity at this point, just imagine if you want to measure the velocity at this point. So what will you do? You will just see the x-axis. For example, this is 0 1 2 3 third minute. Okay, so at third minute you want to measure what is the velocity, or you can say at fifth minute, right? So at this point, this is the fifth minute, and velocity, you'll just go to the y-axis and see what is the velocity values, right? And you will just come up at this position and you will stop, and you will see the respected y-axis value. Say for example, it is 10 meters per second. So you will say that at fifth minute the velocity is 10 meters per second, isn't it? So that is what is the instantaneous velocity, what we are counting by measuring this graph or looking at this graph, right? But what are we doing is, we are decomposing this instantaneous velocity into two velocities. The first one is this particular distance or this velocity, that is the time average velocity, which is represented with u over bar, right? So that one, plus you will be adding this distance, that is the fluctuating velocity, right? So if you sum up this distance, that is this velocity of over here, imagine it is 8 meters per second, and this will be 2 meters per second. 8 plus 2 is 10. That is what we are doing in this particular decomposition of the velocity, right? And that is what is mentioned over here. We are converting the instantaneous quantity into time averaged or fluctuating quantity, right? So this is the time averaged plus the fluctuating quantity. All right, now let us come back to our ANSYS manual over here, and we can read from here that the Reynolds-Averaged Navier-Stokes equations govern the transport of average flow quantities, with the whole range of scales of turbulence being modeled. The RANS-based modeling approach therefore greatly reduces the required computational effort and resources. So with the help of this technique, we are greatly reducing the required computational effort. So if we are, if we are unable to average our results or average the variables or quantities, then it will be quite complicated and it will be quite computationally expensive for us to solve these kind of flows. That means the instantaneous velocity fields, right? Because it has a presence of huge number of small scale eddies which are immensely fluctuating. We are just trying to eliminate them. We are modifying the equations and we are getting a time averaged velocity fields or time averaged quantities, right? And it is widely adopted for practical engineering applications. An entire hierarchy of closure models are available in ANSYS Fluent, including the models which we have discussed previously. And the RANS equations are often used to compute time-dependent flows whose unsteadiness may be externally imposed or self-sustained. So this is what is RANS equations. We are just converting them, we are decomposing them, and we're just trying to solve the flow in a less expensive manner, right? And there is another technique apart from RANS technique that can help us to that in this RANS technique, basically RANS equations, we are time averaging them, right? Apart from time averaging them, there is another technique with which we can simplify the NS equations, and that technique is the filtering technique. So this technique with respect to the RANS equation is the time averaging technique. You can see it is called as Reynolds averaging. And the other technique which can help us to kind of reduce the what do you call fluctuations, and the technique is called as filtering technique. So I have never used actually, because it was never an application for me to go into such amount of computational power and solve the cases. So whatever the cases which I have dealt so far, I have just worked with the RANS equations, and that are enough for a beginner and for a medium level person to work with these cases. But if you have the computational resources, then you can definitely go with the LES approach. That is the best approach, and that will give you more precise results actually. I mean, the results what we get from RANS equations are also widely accepted. It's not like RANS is completely waste thing. It's not really like that, but the quality and the what do you call, I'm just getting short of word actually, the improvement in the flow visualization can be much better if you're just going with more higher more computationally powerful equations, right? So LES is one of them actually. And the filtering is adopted with LES approach, right? So this is basically called as large eddy simulations. All right, now in this technique we are providing an alternative approach. That is, we are not using the averaging technique, and we are basically using some filtered Navier-Stokes equations. All right, so we are there is a mathematical process of filtering actually, and this is quite complicated if we are discussing with respect to equation point of view. So we are just discussing theoretical, and we'll just try to understand a little bit about that as well. Okay, so what is the rationale between them? The rationale behind LES is that by modeling less of turbulence and resolving more, the error introduced by turbulence modeling can be reduced, right? So in the RANS equations, we are modeling the turbulence, right? We are not we are not solving it. Okay, we are just trying to model it, and in this case we are modeling less of turbulence, but we are resolving it more. Okay, so that is a difference, right? So in this case, what is happening in the modeling of turbulence, there are possibilities, there can be some errors in the modeling of the turbulence. But in this LES, because we are resolving more and we are modeling less, then you might be having the reduction of error comparatively more in comparison with the RANS equations, right? So the error introduced by turbulence modeling can be reduced. That is what is the benefit of approaching with the filtered Navier-Stokes equations. It is also believed to be easier to find a universal model for the small scales, since they tend to be more isotropic and less affected by the macroscopic features like boundary conditions than the large eddies. Filtering is essentially a mathematical manipulation of exact Navier-Stokes equations to remove the eddies that are smaller than the size of the filter. All right, so this is a mathematical manipulation, as I mentioned to you when we were discussing about it, that filtering is a mathematical manipulation of the Navier-Stokes equations to remove the eddies which are smaller than the size of the filter. which is usually taken as a mesh size when spatial filtering is employed, as in ANSYS Fluent. So like Reynolds averaging, the filtering process creates additional unknown terms. As I mentioned you that the conversion of when we are time averaging, we will be having an unknown variable which has been erased, and that has to be modeled with the help of turbulent models, right? So these are the turbulent models which we commonly use. But here also we will be having where was I? Yeah, uh, I'm sorry. Like Reynolds averaging, the filtering process creates additional unknown terms that must be modeled to achieve closure. So we are having the generation of additional terms over here also, but in order to solve that, we also have to model them. But just remember, the modeling of turbulence is lesser in comparison with the RANS equations in the LES approach or the filtering approach, right? We are trying to resolve those eddies, and we're just trying to solve them directly as well, right? This is what is the theoretical differences between them. And I believe we have just understood about this, and we can also just see over here a little bit. Now if you can see that the RANS modeling averaging, after decomposing the velocity into mean and instantaneous parts and time averaging, the instantaneous NS equations may be rewritten as the RANS equations. So this is the modified form of equation, and you can see this term which is being circled over here, Rij, right? And this is basically called as a Reynolds stress tensor. The Reynolds stresses are additional unknowns introduced by the averaging procedure. So as we were mentioning so far continuously over here, I'm really sorry, as we were mentioning over here that we are converting them, and because of the modifications, we are having some additional unknown variables, right? So this is what is being arised over here, and that is introduced after averaging the exact Navier-Stokes equations. So this unknown variable must be modeled, hence they must be modeled in order to close the system of governing equations. So if we just have to model this with the help of turbulence equations, and we can then close the complete governing equation, so it will be a valid closure of the governing equations, right? So for closure of this particular governing equation, we have this stress tensor being arised that is unknown to us, and we are utilizing the equations or the modeling turbulence models we are basically using, and those are again set of transport equations which have respected values, and that will be basically helping us to model and to derive the particular unknown variable, right? So this is all a basic discussion about the turbulence modeling. I have not gone into much detail, hence again I believe that I've taken a lot of time for this video as well. And I will be attaching this particular video. I just ask you, I request you to just go through it. If possible, we can just have a random quick discussion. So this is laminar, this is transitional flow, and this is turbulent flow. Then we have the discussion of Reynolds number over external flow or internal flow. You are probably aware of it. So this is the difference between the computational approaches. I mentioned to you about RANS. So this is how your RANS contours will look like. RANS are nothing but the Reynolds averaged NS equations, and this is the LES equation. So you will be having the possibility of visualizing the eddies which are present, and then the last approach is the direct numerical simulation. This is it is expensive for a normal we cannot directly solve in our system, to be honest. It is it is written over here, the cost is too prohibitive, not practical for industrial flows. So industrial flows, in the sense, if you are trying to model a flow over a missile, right? So in that case, or a flow over an aerofoil, right, or a combustion flow. So in those cases, all these industrial applications, you will be having a complex velocity field with plenty of turbulence, and if you are trying to resolve the complete turbulence, small eddies which are present, that will add up to a huge computational time. So it is quite difficult for us to go with that thing. So these two are possible, and we will be sticking to the RANS basically. Okay, so Just remember the RANS equations are utilizing the time averaged Navier-Stokes equations. The LES equations are utilizing the filtered NS equations, right? So a little bit unknown. Again, after filtering as well, we'll be having some unknown variables being arised, and those are modeled. But here, everything is modeled from the start only. That is the difference between, that is the general difference between both of these, right? So this is the most widely used approach for industrial flows. You can see in this block, and this presentation is made by ANSYS itself, so I have to give the credit to them. I'm not making this presentation, I'm just trying to share it with you. Then we have the complete turbulence models which are present over here, and you can see as we are moving down from top to bottom, again these equations are again these turbulence models are equations basically. Those I'll be showing you as we proceed. And like for example, the first one is one equation model, then these are the two equations model, and we are proceeding, the number of equations are increasing and the complexity to solve them is also increasing. So these are the RANS based models, and it is written over here that increase in computational cost per iteration as we are proceeding down. So these are the general usages of them, and this is how the screenshot of the Fluent solver will look like. We can see when we are working on it. And this is about the turbulent boundary layer. I will be discussing about it in the future, do not worry about it, because this is again an important topic, something related to y plus and wall functions as well. So we will be discussing about this as we are proceeding with applications, because at this moment, if I am discussing about this will be going above your head, right? Provided if you are a beginner in ANSYS, Fluent, and if you are already aware of the software, then I'm really sure that you are a little bit aware of the wall modeling techniques which are present and which can be chosen to proceed for our simulations, right? So I'll just stop the video over here. Let us move to the next video.